Good afternoon, everyone. My name is Ruby Yi, and I will be presenting on a project titled Estimating Turbulence in the Arctic Ocean at the Canada Basin Shelf Break. Let's start by defining turbulence and why it's an interesting topic of study. First of all, it's an important phenomenon by which mixing occurs, as you might be able to tell from this animation of a turbulent flow. In the ocean, we mostly focus on how turbulent mixing erases density gradients. And why do we care about mixing? Well, mixing is relevant to many areas of ocean research. It influences distributions of nutrients, chemicals, cold and warm water masses, the list goes on. I'll note here that there are other ways by which mixing can occur, for instance, double diffusion, but in this talk I'll focus mainly on turbulence. It's difficult to attach an exact definition to turbulence, but a defining feature is these chaotic, swirling motions called eddies. The energy needed to sustain this kind of motion comes from inputs like wind, tides, and breaking internal waves. In particular, we see that turbulence is often enhanced over rough or steep bathymetry, and notably at continental shelf breaks. When energy is input at large scales, say from an internal wave breaking, it's transferred down through eddies to the smallest scales. This is known as the turbulent energy cascade. Eventually, we get eddy length scales small enough that molecular diffusion becomes important, as this is where the viscous dissipation of energy occurs. We say that viscous dissipation occurs at the Kolmogorov length scale. When we say that we want to estimate turbulence, we really want to measure the eddy diffusivity, which quantifies how much mixing happens because of turbulence. To get the eddy diffusivity from real data, we also need to estimate the dissipation rates of turbulent kinetic energy, known as epsilon, and temperature variance, which is chi. Temperature variance might seem a bit unrelated, but I'll explain why it's important for the data that we're working with specifically. Something really remarkable about turbulence is that the turbulent spectrum is universal. What I mean by this is that when a fluid is turbulent, its spectrum in frequency or wave number space is very predictable. Theoretical forms for the spectrum, which are now widely accepted, were deduced by Batchelor and Craiknen in the 1950s and 60s. The spectrum here on the screen is of kinetic energy, but you can also have spectra which follow a similar form for shear or temperature gradients, which is what I'll be showing you in a few slides. Although turbulent spectra for different parameters differ slightly in shape, they can all be related via dimensional analysis. Again, notice here that energy cascades from large scales at low wave numbers to small scales at high wave numbers. This was a lot of information, but the gist of it is this. The universality of the turbulent spectrum is pretty remarkable, but it's also very convenient because it enables us to make estimates of turbulent parameters, and here is how. So first we fit the universal theoretical spectrum to our data. Then we calculate chi, the dissipation rate of temperature variance, which comes from the integral of the temperature gradient spectrum. Then we can calculate epsilon, the dissipation rate of turbulent kinetic energy from chi, and then finally we can calculate the eddy diffusivity, also known as the turbulent diffusivity, from epsilon. Recall that the eddy diffusivity quantifies the amount of mixing happening because of turbulence. So all of these parameters are important in quantifying turbulence. Turbulence plays a key role, and historically an understudied role, in ocean mixing. And as I touched on earlier, why do we care about mixing? Well, different subdisciplines of oceanography probably have their own reasons for caring about mixing. But to name a few, it impacts nutrient and other chemical distributions throughout the ocean. For instance, it could be a driver of mixing from the deep ocean up to the surface. It can influence phytoplankton distribution and density, and it drives the mixing of warm and cold water masses, which influence global currents and, in turn, global climate. Now with this turbulence background, I'll spend the rest of the talk discussing the project. Our data comes from a 2018 research cruise in the Canada Basin in the Arctic Ocean. You can see here, this is the coast of Alaska in gray, and the dense contour lines indicate the shelf break. Most sections here cross the shelf break. We attached an instrument which samples temperature 512 times per second to a CTD rosette. So we have high-resolution microstructure temperature profiles at all of the locations indicated on the map. Usually turbulence is measured with shear probes, and this is a bit of an obstacle because you need specialized profiling platforms. The vibrations from a CTD rosette, for example, would contaminate shear data. So instead here, we're using temperature variance as our tracer. It's like the thing we're observing that gets mixed due to turbulence. And this is why that parameter chi, the dissipation rate of temperature variance, is important. We use our microstructure temperature gradients, which should, and luckily they do, look very similar to the universal turbulent spectrum. Now, when working with any instrument, it's hard to know the exact difference between the environmental variability and what the instrument sees. For our temperature probe, we have to address some uncertainties, especially when looking at phenomena at small length and time scales. For instance, we ask, how long does it take the probe to detect a temperature change? This depends on the thickness of the glass tip, which varies between individual probes. What's the smallest length scale of environmental variability that the probe can resolve? And this depends on the length scale of the probe tip itself. We also have to consider how the fall speed of the probe on the rosette and the instrument noise affects resolvability. For all of these reasons, we are pretty confident that we don't resolve the smallest scales and the highest wave numbers. So the solution is to fit theoretical spectra to our partially resolved data and then work with those. There are two ways that have been used in the literature. The first of which is to fit only to the range of our data that we can confidently resolve. This is known as the chi-pod method. The second way is to amplify our data using an estimated function which compensates for the instrument response, and then fit to the whole spectrum. This is known as the mean likelihood estimate, or the MLE method. On the right is an example from our data. These are the observed temperature gradient spectra from our two probes, and these are the theoretical fits, here made using the chi-pod method. You can see that the observation is poorly resolved at high wave numbers, small length scales, compared to what we expect it should be. So we would say that the observation rolls off early compared to the theoretical spectra. Each method operates on a fundamental assumption. The chi-pod method assumes that the rate at which density is mixed is equal to the rate that temperature is being mixed. That is, there are no other mixing processes than turbulence. The MLE method assumes we know how to compensate for the instrument's poor resolvability at small scales. In practice, this is difficult to determine accurately since individual probes vary and it's impractical to calibrate every one. Here's a comparison of how the methods actually perform on our data. Every measure of epsilon, determined using the chi-pod method, is shown on the x-axis, and the MLE method is on the y-axis. Note here the thin blue 1-to-1 line. So we see that the MLE method tends to overestimate comparatively when epsilon is small, or when turbulence is low, and the chi-pod tends to overestimate when epsilon is big, or when turbulence is high. So a large part of this project is just understanding why and under what conditions the methods differ. Regardless of method, we need rejection criteria to eliminate contaminated data. So for instance, this could be places where the CTD fall speed drops abruptly, which are often contaminated. So here's an illustration. The CTD, represented by the gray cylinder, with temperature probe mounted at the bottom, is falling at some speed v1, and it carries water within its frame that's also moving at the same speed. Then if the CTD slows to some v2, the inertia of the water within the frame, still traveling at v1, causes it to overtake the probe. So now the probe is seeing this contaminated water, which tends to have falsely high turbulence compared to the environment. In our data, it looks like this. So in the area between 60 and 70 decibars on the middle panel, you can see that fall speed decreases abruptly, and it actually dips below zero, which represents a brief direction reversal. So as a result, we see a spike in high epsilon, so that's like saying a spike in turbulence in the left panel. Using a fall speed threshold, we would reject the points indicated by the dots here, such as these. Now here's an example of some results. These are epsilon profiles for one section near Barrow Canyon. The solid gray is the bathymetry, and you can see that it drops off at the shelf break. On each profile, the two blue curves give epsilon from each method. They differ in magnitude at times, but generally they follow the same shape. The red dots show indices that were rejected based on low fall speed, and also on our own measure of fit. Something interesting here is that we think we see elevated turbulence near the bottom. So for instance, at these locations, there are slight increases. This is what we expected, since the shelf break is a known location for turbulence generation, because of internal wave breaking, as I mentioned earlier. Now, our epsilon range is quite big. Since we're still fine-tuning our spectrum rejection criteria, it's very likely that the higher epsilon, say 10 to the negative 6 and bigger perhaps, are not real. More likely, they're probably from contamination due to the CTD or other mixing phenomena. But comparing our orders of magnitude for epsilon to other published ranges from the Arctic Ocean, which you can see on the right, we see general agreement. That is, these ranges all fall within what we have observed. So to wrap up, I want to emphasize that the main goals here are developing a reproducible methodology. There aren't currently many turbulence observations available throughout the global ocean, since they usually require specialized sampling platforms. Using the microstructure temperature profiler attached to a CTD is somewhat new, and if it became the norm for turbulence measurements, it could enable much cheaper and easier measuring than is widely available currently. And that's not just in the Arctic, but on research cruises all around the world. And having more turbulence data available means we can more accurately quantify mixing, with the big picture goal of improving ocean models and even climate prediction. Now that's the end, and I look forward to answering any questions you might have. Thanks for listening.